Yeah. Okay, then I'll go to the part about node running. So what we've done, I'll share my screen. The entire thing. So if everyone checks it out, what we've done is we've provided some documentation now on how to set up a node. There are multiple ways of running a node. You can compile it from scratch. You can run it in a virtualization environment. You can do it in a cloud service when you compile from scratch. But this is a pretty involved process. So if you're not really technically inclined and don't have the dependencies installed and don't know how to do it, it's not that simple. I must say it's become a lot easier versus what it was before, but it's not super straightforward. So there is a Docker image. This Docker image has some caveats. And for now, it primarily focuses on a local node setup. So that's a node that you can attach to with the wallet and that you can then do transactions with without others connecting to it. So people that are interested in doing it from scratch, there is documentation for it. We'll post it. I'll just post it now. I wouldn't recommend doing this, taking this approach. So if you want to set up a node from scratch and compile it yourself, there is this piece of documentation. And then what we'll look at today is the Docker way. If you want to use Docker, it's documentation.
I'll make a new FAQ section, Hein, and then I'll put it in there as well, just for it to be more official for everyone.
Yeah, you can remove my post and then just repost it with this information. So this
Possibly
Docker setup.
Removing your post.
I'm fine with it. So this Docker setup is really easy. What you need is you need to have Docker installed, of course, an internet connection. Optionally Git, but it's not used necessary anymore with this setup. Terminal access and an x86 processor architecture. So this won't work in its current form on a Mac. At least on a Air Macs, the newer Macs, yeah. So this current setup is an old one that assumes that you use a repository and build the images yourself. But we also have an image published, and it's really simple to run this. All you need to do is pull, if you have Docker installed, which you can check by doing docker v, is docker pull hdauven /rusk. What will happen is it will pull in the Docker images. I've already got it installed. And all you need to do then is run this command, which will just basically start one up for you. A Docker. I never had to do sudo, but hey.
Are you in the Docker group?
Yeah, I should be. This is demo hell, right? Do you have Docker installed?
I do, sure.
Could you try this out? I've updated. I've updated my thing recently, so it.
Oh yeah, it happens all the time when you update the daemon. It simply stops working without a restart.
Well, I could check out if the daemon is still running.
It's hdauven Docker, right?
Yeah, hdauven /rusk. I'll post the Docker image for you.
Yeah, it has it.
Okay. Yeah, it's a demo effect.
Classic.
And yeah.
Sure. So here's a terminal. Let's see what would happen. So, boom.
Yeah,
this
this
is, by the way,
could
fresh.
take a while.
So, apologies
this is
for
really
that.
fast.
Yeah, and Well, the download completes fastish. My interwebs isn't that great.
Yeah, so the thing is, if you build it from scratch, it will build like 11 gigabytes worth of data. So it's pretty big. It takes like 15 to 20 minutes to compile everything. But with this image, and if you shouldn't take that long to pull this in, because I don't have Docker working at the moment, I can demonstrate with the updated wallet CLI that you can do transfers at the moment, which is sad. I'm not sure, Ed, if you have wallet CLI with the latest
I
version.
don't have the wallets installed.
Okay.
I'm sandbar. The demo effect. Amazing.
Yeah.
So it's literally just a Docker pull and Docker run. That's actually quite nice.
Yep.
Yeah. Well, technically, I think if you do only a Docker run, it would work anyway. So you could minimize this even.
Yeah, you could, in theory, could run it with just one single command.
Yeah.
The thing is, with this current node setup, it's a short-lived node. So this assumes that you're not going to run this for the long term. There are some caveats with running this Docker image on Windows and Linux. It's partially solvable, but we built the node software with Linux in mind.
So indeed, should we assume that we'll be posting instructions to like make transactions against the node and all of that, or are those already posted?
Those currently aren't posted.
Okay.
And that's part of a bit of a wider documentation effort, right?
Yeah.
There are some, because we currently have communication between the node and external software through WebSockets. There's some effort going into making that HTTP only, right?
Mm-hmm.
So currently, if you want to connect to a wallet, you need to enable WebSocket listening. That's not documented in the README. I don't think there's currently a README that explains how you can connect both, but it's really a really simple process.
Yeah. Okay. So let's try and run this with the command you posted. Oh, look, a node. Looks familiar.
Yeah, it's that simple. And maybe you can do this. No, never mind. I can run it. I can run it locally and then just set up an actual node as well, a compiled one. Benefit being that we can connect a wallet because I have the wallet installed.
Mm-hmm. So indeed, you can see the consensus loop going around. It's with itself, so it's as fast as can be, let's say, per block. But in a real network, this would be a bit slower and include transactions. So
Yeah, so one of the things we also did in this is we set the delay time, we set that really low. And you can do that when there aren't that many nodes involved. But when there are more nodes and the message propagation throughout the network might be a bit longer, it might not be the best idea to do it.
yeah.
Okay.
Maybe while you're setting up the node to make transactions and all of that, we can jump to showing what smart contracts look like, what they can do. I think it's
I
you have it set up. All right. You are muted though, so I'm not sure we can hear you.
No longer. So let's see. So on one side, I'm running the node now. On the other side, I have my my wallet. It's compiled. How to do that? It's available on the GitHub repository, right? When you run this piece of software, you have to say that it should connect to a local network. So there is a network parameter you can pass it, and it has multiple options. But since you're doing this locally, you put it to local, and it will connect to the local node you have. So if I access my wallet, offline, I am online. Okay, I think I broke my computer. Yeah, build. Okay. Well, I'm having a lucky day today.
You're borked.
Yeah, I'm borked. That's really interesting. Borked it myself. Oh, it should work. Yeah.
No. No.
Yeah,
There
yeah,
it is. Okay.
Yeah. So, I have an address here. I'm connected to it. It can see the state. It can see the transaction history. Something we didn't have before. I do need to purge my state. Something I haven't done. So let's see. Remove. Let's not do this one, but Dusk wallet cache. Yep. Connect. And the cool thing is we have a couple of new features in the wallet CLI. So if this logic applies to the wallet CLI, it will also apply to the web wallet. And that is that it can now recover the addresses that you already have funding on or a wallet history with. So that's really nice. It doesn't get lost, or at least you don't have to restart everything from scratch. Partially, this is because we have a new format with our wallet file, which saves which addresses already have been used by you. So if you use one around, it's really nice to recover wallets with funds. Let me transfer one. This is all done locally, right? Even approving all of it is done locally. And this happens really fast. Yeah, so I've sent funds on display directly because it's waiting a couple of blocks. It's also nice maybe if you could see if a transaction was included. Oh, it's here. Yeah. So in this block here, a transaction was included, and I should at some point see that I sent funds. Yeah, I've sent a small amount of funds, and this is all locally. Yeah. So it's really, in my view, it's really easy to do this. If you write it out, it should be easier for everyone to follow. And I think we're now going to do another more exciting part of a network, and I'll hand it over to Ed.
I'm not sure it's more exciting. It depends on who you are. Like for people who actually want to have their money on Dusk, this was more exciting. But for people who want to make contracts that want to make programs for the network, this is, I suppose, more interesting.
Yeah. There are a couple of questions. I'll answer them quickly. So copy the Docker image and run it. Yes, that's it. If you want to run a local node that will not store state and it doesn't connect with other nodes in the network, we can change parts of this to work, right? Like we can make this Docker file that we currently have more extensible. It will just require a couple hours more of work. Does it replace the ITN installer? It can. And this is currently just a single node not connected, and we can do that.
Yeah, that's the thing. It doesn't connect to the wider network yet.
You can do this on Linux.
Right.
You can do this on Windows and Mac, and that is because of an issue in Docker.
Yeah. Host network and all. All right. So the goal I have with showing you this bunch of code that you see is to get you a little bit acclimatized with what smart contracts look like in Dusk. So to set a bit of the stage, a smart contract is nothing but a program that gets run with a given set of data and manipulates some state. Yeah. So it exposes functions, it imports functions from the host, and we'll see all of this a little bit in action. This is the simplest contract that I can think of, except with the exception of a contract that does nothing. This is a contract that has what's called a box in there. And the box is a pointer to some data that is on the heap. So you can see here a bunch of imports. You will need to be slightly familiar with what Rust is and how it works. So the word struct and box shouldn't be totally unfamiliar to you. But so what we do here is we declare a structure, which is this box, and we make a static. So this is something that will exist for the lifetime of a program that starts out being a box with nothing in it. And we will want to expose two functions, and that is one to set the value in this box, and another one to get the value in this box. Yeah. So as you can see with this code, okay, so if this box is something, we mutate the value. If it is nothing, we simply set the value. And with get, we simply say, okay, return the value of the box if it is anything. You can also see these two functions here, defined on the global scope of the library. These are the functions that are called by the host when the contract is triggered. So when the contract is triggered, the entry point is this one, or any other functions you might want to. If you want to see more of these examples, feel free to look into the PyCrust/contracts. I see someone saying they don't see anything.
No, I can see it fine.
You can see it fine. Perfect. So it's not on my end. Yeah. Feel free to look at the examples that are in PyCrust/contracts. There's a bunch of them that we use to test. Feel free to look at those if you want more advanced examples that are going to be shown here.
Sorry, Ed, I have a question.
Please go ahead.
We have this concept of a host.
Yes.
This is not something that's familiar, I think, in other blockchain projects when you develop for them. Could you expand a bit on it?
Yes. So the host is the program that runs the contracts. So it is your node. Your node is the host. And the node has to provide some functionalities to the contract. There's these things called host calls, which are essentially the contract interrupting, awaiting for the host to give them something, and keeping on going about its business. So the host, I'm talking about the node.
And when you say interrupting, this is a concept that's also not common. And the reason for this, something that would maybe be valuable to explain, because you have a virtual machine on one side and a host on the other. And a virtual machine is expensive, right, to run computations in.
I think we need to be careful a little bit with the nomenclature. So a smart contract is a program, yes. So when this is compiled, we use WebAssembly. So this gets compiled into a WebAssembly file. And the virtual machine, which, by the way, is the host. So the thing that is running the virtual machine is your node, and your node is the host. Picks up this program and gives it some things. So it's if you want to compare this to other chains, it's actually fairly similar. So in Ethereum, you will have a Solidity smart contract, for example. This will be compiled into Solidity bytecode. The node ingests this Solidity bytecode and then gives this program, this smart contract, a bunch of functionality that it can access. So the concepts are equivalent. It's just we use different nomenclature. And the reason for this is that it actually comes from the WebAssembly spec. So a host, is the thing running the WebAssembly program.
Yeah, we use this in multiple places, right? We have a very clean mapping from WASM concepts over to our virtual machine.
Yeah. So these functions are the functions that are available to be called by the host and by other contracts as well. So the host, meaning if you submit a transaction, you will be able to call either one of these. This is what this means. Yeah?
Mm-hmm.
So how do we call this, right? So in the internals of our virtual machine, you can literally see, like, we start a virtual machine. We start a session with the virtual machine. What these sessions are, it's a little bit out of scope of this, session that we're having here. We deploy the contract, and we call the get function of that contract with no arguments, because get doesn't want any arguments. And we can see that we can get values from it, we can set values, and this is all hunky-dory. So this is kind of the simplest contract that I can think of. You can write these in Rust. You use the PyCrust uplink library, and to look at how to compile these, you can go into the PyCrust repository to see how that works. Actually, I can show it to you right now. There's this complicated compile command right here. Actually isn't too complicated. Or do you think it is?
Our perspective. Like, I can imagine that people who've never seen this before.
Yeah, this entire makefile is a little weird, but the cargo build command is very familiar to anyone who uses Rust. A manifest also. I think everyone understands the concept of color. These are a little strange. They can be explained if anyone has questions, but target WebAssembly.
I have one question about the struct and the state definition. That's something you also don't see that often, right?
Indeed, yes. So you have to understand that Rust is not a DSL for smart contracts. Yeah,
DSL being a domain specific.
a domain-specific language. It's a general purpose language. So there have to be some things if you're coming from a general purpose language, that you actually will have to constrain so that this works in the environment that is going to be inserted in. So this state here that we define is essentially just a variable that is going to be put in as data in the WebAssembly payload. So if we compile the contracts here, and we actually use WASM tools to print out the WebAssembly so that we can look at it, not the counter contract, but the box. This is what our contracts look like in a textual representation. Yeah, so we get a huge binary deployed into the chain. This is what they look like. Completely intractable. This is why this is better. But in the end, you will see some data that is going to be set at the beginning, at the instantiation of this contract, and that's going to contain this.
So that's the interesting thing about this structure is you define yourself how the state of your contract looks like.
Absolutely. So whatever you can represent in Rust, you can represent on chain.
Yeah, and that gives you a lot of freedom.
It's immensely powerful. It does come with some caveats on our end, but that's for us to solve. Yeah, so essentially what the most basic contract writers are going to be just doing a few things. First, they're going to be defining the state of their contract. What does it look like? What kind of structure is it? Is it one structure? Is it multiple structures? You could think of a contract with multiple things that it keeps. I don't know, could keep like another state like this. It's totally fine. No reason why not. And you're going to define some mutations on it. So something that you can use to mutate the state, something that you can use to look at the contents of the state, and you're going to expose these functions. And then you are actually done.
This exposure, this looks like duplicate code. Is it possible to abstract this away?
We are still having internal debates as to whether we should or not abstract these away, but it is possible. You can think of something like a macro here where you would say something like contract, and then this code would be auto-generated. This is possible, absolutely. Should we?
Let's see what a poll
I'm
does.
not sure.
Yeah, let's see what a poll does.
Yeah, should we do this or should we not? You guys answer. I have my opinions. Some people have theirs, and this is how this works. But actually, what I wanted to, do you have anything? Sorry.
Yeah, so there are. I think you want to go to the private.
Yes, exactly.
Yeah. Before we do that, there are a couple of questions and statements.
Where can I see these? I'd like to see.
Well, they're in different places. So there's one in this chat that says, "Hope you removed random numbers." From Smith.
What? Which random numbers? Where are you talking? Which ones are you talking about? Smith.
All of them.
All of the random numbers. There are no random numbers.
Random number generator.
Oh. Is this because of the Telegram conversation or something?
No,
I mean,
I think because of the limits of how we can set things up, right? Like the constraints we we can put on the system.
But
I
which
think it
random
matters a bit
numbers?
on. Yeah, I think it also depends a bit on the context whether it's could be problematic or not. He says
Okay,
determinism.
so
yeah.
he is talking about determinism. Yeah, all of this is indeed deterministic. There's no randomness in here. Once the contract is compiled, it is simply that piece of code, and once executed, it produces a certain result. So there's no randomness from the host or from anywhere. But we can explore that in a little bit, if you want.
There are some other questions. So, what application would this contract have?
This one in particular, I can't
Yes.
see much. This one is so tremendously simple that it just has no application. But the next one technically sort of does.
The
So
building blocks.
yes. So this is just to show you this is what this contract does. This is how to write them. As you can see, it's not incredibly complicated. The simplest contract, 50 lines, and it's not even that simple. And you could conceivably deploy this to the Dusk chain.
I've got one more question for you.
Go ahead.
And then you can go to the private contract. This contract has no privacy, right?
No.
Except
As
for
in what A is, what's on the state is visible to everyone. Yes? So
yeah.
everything that you put in your contract state is not private, just as a disclaimer. So anything that hits this will actually sort of get stored on disk. Yes? So there's no privacy here whatsoever. But we can see how you can, by using the power of zero knowledge proofs, you can actually have privacy. But this is a different question. But indeed, this is not private. Nothing about this is private.
This is a public contract, so everyone can call the SEP function, but the caller is not known, right?
Correct. So one of the features, features, actually sort of non-features, things we do not do, is there is actually no such thing as a caller. So the functions that are available to us through uplink are the host will not provide you caller information. So indeed, you cannot say this person is calling me or this wallet is calling me.
Which is really interesting in itself.
Yes, I would say this is a subject for a larger set of questions, but we could indeed explore this.
So I do have a question for both of you. I know that you're going to go a bit forward with this as well. So the notes to be easy to run, but for example, the smart contract I'm looking at, a person who doesn't have any kind of background writing smart contracts, like me as an example, how easy would it be for me to actually put down even a basic structural, smart contract as an example? Do I have to follow like documentation or something that can help me to kind of write one as an example?
Well, at the moment, yes. There's no. So if you have no technical knowledge whatsoever, you're going to find it difficult to write a smart contract in general, since they are programs. So you should at least have a cursory knowledge of programming, such that you can do so. But we don't currently have extensive documentation about this, simply because we also don't expose the deployment functionality currently. So we will do this in the future, obviously, since it's one of the main functions of our network. But yeah, you do need to be a programmer to understand what you're doing. Don't
Okay.
write smart contracts, especially ones that hold value, like hold some sort of thing that you can pay for, if you have no knowledge of programming. I discourage this.
Yes, and
All right.
seconded. I think one interesting thing is that at some point, if we have standardized contracts, you could get to a point where you have builders where it is relatively easy to deploy. You have this sort of stuff in Ethereum already, like with ERC20s and that sort of stuff, with NFTs, that you basically build wrappers around the parameters you set on a smart contract, and then can simply deploy it. But you wouldn't be writing them yourselves.
Yeah, that's some sort of template contract, and we are thinking of doing that with Zedger in the future, so making them easily deployable as templates.
Yeah, that would be really nice.
Yeah.
Thank you.
But then who writes the contracts is a programmer, and you deploy the contract a template instead. All right. So I know there's a lot of curiosity as to how zero knowledge works in conjunction with this. So since this is all visible, like I can see I can query it, anyone can. How is this privacy preserving at all? Well, you need to switch up what you think of privacy preserving a little to understand. So this is an example of a contract that calls functionality that is defined by the host, meaning it calls a function on the host. Yes? And what this function on the host does, in the case of verify proof, is we as a contract receive two things. We receive a proof, and this is what's called a zero knowledge proof. This is a plunk proof, if you've heard this term before. And you receive a bunch of things that are public. So public inputs. This is a vector of scalars, and you can think of scalars as just a number. They're numbers in a specific field of a specific mathematical curve, elliptic curve in this case. But you can think of them as just numbers. And what this function of this contract is going to do is it's going to grab this proof, grab this public inputs, and pass it to a host function that's called verify proof. Well, this function in turn receives this proof, receives these public inputs, and is going to tell you if this proof is valid with this given public inputs. And you, as a contract, then get to branch. So get to just make decisions based on whether this proof is valid or not. So in this case, if the proof is valid, I'm returning a string saying proof is valid. If this proof is not valid, I am returning a string saying this proof is invalid. So, but what is this verify proof here? Like, what does it do? Well, this is a function, like I said, offered by the host. So the only thing that it does is it's first going to retrieve what it's been passed, and then in the end is going to simply verify. It's going to grab the verifier. You need to be maybe a little familiar with cryptography in general. So you can verify, as in the same way you can verify a signature, you can verify a zero knowledge proof, let's say. In a signature, you can verify a signature with a public key of someone. And with a zero knowledge proof, you can verify it with, well, very aptly named verifier. So you pass this verifier the proof and the public inputs, and we return in the end whether it is valid or not. But what are we actually proving here? Well, in this case, I defined a really, really simple circuit. A circuit is what we use to define the thing that we are trying to make a proof for in Plonk. And in this case, the intent of this circuit is to be able to prove that I have a solution for this very, very difficult equation right here. It's A plus B equals C. So given a number C, which we are going to consider public, and we are going to pass to the contract, I am going to prove to you that I have an A and a B such that this is true. Yeah? There's probably going to be questions about that one. To make this a circuit, I have to implement what's called a trait in Rust, the circuit trait, which takes in a composer, which allows you to, well, define the circuit. And we append both of these inputs as private, so append witnesses, and we make what's called a constraint. And you can see this will be in the main branch soon, so you can look at this on your own time if you like. But this equation collapses to A plus B equals C, and we append this gate. So it's a scalar, quite thinker. It is around 2 to the 256 bit. So you can have quite a few numbers here. Yeah, so that's how we define the circuit. And in the end, the contract is only ever going to receive C. So as a test here, what we do is we generate a proof that we know A and B. So we do know that 2 plus 2 equals 4. We generate this proof. Yes, there is random numbers here, by the way. But we only ever pass public inputs, and this public inputs contains C only. And the contract should return to us that this proof is valid. And it does. We can run the test if we want. So this test is called host proof. And it succeeds. Wonderful. But we also assert that if I pass in a wrong proof with wrong public inputs, I receive that the proof is invalid. So notice, like if I actually print out public inputs, that we only ever have, this is going to pass, so it's going to need no capture. Yeah, that we only ever will have one element in the public inputs array or vector, and that is C. By the way, this is 4 as a BLS scalar, so this is a little bit intractable. Is this actually? No, sad. Yeah. So at no point do I show them the solution. Do I show the contract the solution that I have, which is 2 and 2. A is 2, B is 2. But I do show them C. So you can think of, can an attacker simply try all combinations? Yes, in this particular circuit, it is very simple to find a solution. Yes? So, I mean, all of you can, I would assume. This is also a solution. This is, well, that's the solution that we had, but this is also a solution. This is also a solution. And actually, that's about it.
0.
Oh yes, 0, of course. 0, 4 is also a solution. So this would work too. And we can test this. Like it's okay. This will work. At least it should.
Yeah, I think also quite thinker. I think if I look at your comment, you think that, at least I assume you think that it should be difficult to do this, but that's not the purpose, right?
Yeah,
The
the
purpose of
purpose
this is
here
to
is
be
not to
simple.
show you, not to be a really difficult problem to solve. The purpose of this is just to showcase you that you can indeed prove to a contract that something is true without showing all information about said proof. Yeah, that this proof is totally opaque. It doesn't contain 2 and 2 or 1 and 3, etc.
Yeah, for instance, if you want to prove that you're the owner of a certain asset, then the combinations that are possible there will be much more limited.
Oh yes. So in our case, if we want to talk just a little bit about the transfer contract, what you will have is a tree. So you will have a Merkle tree with all your notes, so with all your UTXOs. We'll have some positions filled, some positions not. And you will have to prove that you own the note at this position, and that the notes that you are producing, notes meaning the transaction outputs, actually flow from the notes that you're spending. So in the same way that A plus B equals C, your inputs is going to have to be the same thing as your outputs. So there's no creation or destruction of funds. So there's a bunch of circuits that you can make here that are far more complex than this.
In this example, you're basically proving that you know how to add two numbers together.
That's right. And a primary school, or maybe even lower than that, should know how to do it. Or to how to find solutions to this given circuit.
Yeah, it took me like 3 tries, but that's a different story.
Let's see where to go from here. I think this is it, really. One thing that is good to explore is how we are actually defining this circuit. So in here, this host function that we are defining, called verify proof, only verifies a single circuit. Yes, and that's our test circuit. But so to make it possible for any contract to have privacy in the same way as here, what you would have to do is allow this kind of function to function with any circuit. Yes? And that is what we do downstream. So we actually allow the contract to pass a description of the circuit they want to be verified. So in that case, the contract actually gets to define it, which enriches this tremendously. Because once you deploy a contract, you are effectively defining the conditions under which a transaction is valid, and the same with the proof. Okay.
Yeah. I think that's maybe an interesting one as well, right? Because PyCrust stands on its own.
Yes.
And what we basically do with Rusk, and then I'm talking not about the node, but Rusk as a piece of software, sort of consumes PyCrust and enriches it with functionality.
That's right.
That also integrates with the blockchain itself.
So it essentially does this. So it wraps the creation of a VM with a bunch of functionality. And you can think of functionality like providing the block height, or verifying proofs, or hashing, or verifying signatures for that matter. So that's all things that the node provides contracts. And we will have obviously documentation of this in the future, but now is a little early.
Yeah, and I mean there are parts of documentation out there.
Yeah.
But it's, you need to know what you're doing, and it's not as clean and neat as we all would like.
Yeah.
But that's a matter of time. We're getting there slowly, but
So it's also important to note that you will never write this code. This code, like the code that actually calls the contracts and does all of that for you, you will not write this. That's our responsibility. Or rather, if you ever want to write your own node, you can. But in this case, you don't write this, we do. You will only write this. And as you can see, verifying a proof here is merely like taking them in and passing it to the host. So it's pretty simple.
is it also true for how the circuit itself looks like? So what you're proving here is A plus B is C. Isn't that a part you need to write yourself as well?
That is a part that you probably will write yourself, yes, unless you're taking someone else's circuits and deploying it to our chain.
Okay. Yeah.
You will probably define what the circuit looks like, embed them in your contract, and pass them to the verify proof function downstream.
So if you look at the host file, where you have the circuit defined, you would primarily just describe the circuit.
Yeah. So this structure, you will probably have to if you want to use this functionality, you don't need to, but you can. You will define the circuit, you will implement the trait. You'll probably expose to your users functionality related to this. Like I want to prove that. So I imagine that you might want to show your users like something like prove that with A and B. What's the numbers again? Nebula scalar B. You probably want to do something like that. So this is kind of an API that you would provide your own users. And you would define the circuit indeed.
Yeah. Clear? Let's see if there are any more questions.
Medieval times were indeed simpler.
Yes.
Also far deadlier. So
I'm gonna say, guys, just take a few more questions and then let's just wrap it up.